Tonight, we're going to explore one of the most fundamental questions humans have ever asked. How many stars exist? It sounds simple enough, but the answer is so staggering that it challenges everything about how we understand numbers, scale, and our place in existence. By the end of this journey, you'll not only know the answer, but you'll understand why it matters and what it reveals about the cosmos we inhabit. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. Let's begin with something you do every day without thinking about it. Estimating quantities. When you walk into a room, your brain automatically assesses how many people are there. 5 people? 20? Your estimate is probably pretty good, up to about 15 or 20 people. Beyond that, things get fuzzy. Is it 40 people or 60? Most of us genuinely can't tell without counting. This limitation isn't a failure of intelligence. It's how human cognition evolved. Our ancestors needed to assess immediate threats and opportunities. How many predators? How many members of my tribe? How many animals in that herd? These numbers rarely exceeded a few dozen. We never evolved the mental machinery to intuitively grasp thousands, let alone millions or billions. When someone tells you a stadium holds 70,000 people, you accept it intellectually, but you don't feel what 70,000 means. You can't picture it the way you can picture 5 people standing in front of you. And this creates a problem when we start talking about stars, because the numbers involved are so fantastically large that they exist completely outside our intuitive understanding. So before we can discuss how many stars exist, we need to build a framework for understanding large numbers. We need to feel the difference between 1 million, 1 billion, and 1 trillion, because without that foundation, the final answer will just be noise. 1 million seconds is 11.5 days. You could count to 1 million in less than 2 weeks if you never stop to sleep or eat. It's a marathon, certainly, but it's conceivable. You can imagine devoting 11 days to a task. 1 billion seconds is 32 years. If you started counting the moment you were born and never stopped, you'd reach 1 billion in your early 30s. The entire span from infant to adult would be consumed by this single task. What seemed like a big number with 1 million has become something that spans a human lifetime. 1 trillion seconds is 31,700 years. To count that high, you'd need to have started before the invention of agriculture, before writing, before civilization itself. You'd have been counting when humans still lived in small nomadic bands during the last ice age. Every empire that ever rose and fell happened while you counted. Every war, every peace treaty, every technological innovation from the wheel to the smartphone occurred during your count, and you still wouldn't be finished. The difference between 1 million and 1 billion is 1,000 times. The difference between 1 billion and 1 trillion is another 1,000 times. These aren't just bigger numbers. They're different categories of magnitude entirely. Now here's the difficult part. When we talk about the number of stars in the universe, we're dealing with numbers that make 1 trillion look quaint. We're talking about hundreds of billions of trillions. Numbers so large that even the trillion comparison fails to convey their scale. But we're getting ahead of ourselves. Let's start with what we can actually see. On a truly dark night, far from city lights, you can see between 2,000 and 5,000 stars with your naked eye. The exact number depends on your location, your eyesight, and how long you let your eyes adjust to the darkness. Let's say 4,000 to be generous. 4,000 stars. That's the extent of what ancient humans could see. That's what philosophers and astronomers worked with for thousands of years. And here's what's remarkable. Every single one of those visible stars is in our galaxy, not scattered throughout the universe, just in the Milky Way. In fact, they're all relatively nearby in cosmic terms, within a few hundred light years of Earth. You're not seeing the universe when you look up at the night sky with your naked eyes. You're seeing your immediate neighborhood. The Milky Way is a barred spiral galaxy. Picture a disk with a bar-shaped dense region in the middle and spiral arms curving outward. Our sun sits in one of those spiral arms, about 26,000 light-years from the galactic center. That's roughly 153 quintillion miles, or 246 quintillion kilometers, from the dense core, where stars are packed far more tightly together than in our region. When you see that faint band of light stretching across the sky on a dark night, that milky glow that gives our galaxy its name, you're looking edge-on through the disk. You're seeing the combined light of millions of stars too distant and dim to resolve individually, all blending into a soft, luminous river across the heavens. Everything you can see with your unaided eyes, every constellation, every bright star, all of it exists within a tiny bubble around Earth. The farthest star visible without a telescope is about 16,000 light-years away. The Milky Way is 100,000 light-years across. You're seeing less than 1% of our galaxy's volume. This is where telescopes changed everything. When Galileo first turned a telescope skyward in 1609, he discovered something that shook the astronomical community. That Milky Band wasn't a cloud of glowing gas. It was stars. Countless individual stars, too faint for the naked eye, but perfectly clear through his primitive telescope. Every improvement in optics revealed more. Bigger lenses collected more light, showing fainter objects. Better manufacturing created clearer images, and the count kept climbing. Thousands became tens of thousands. Tens of thousands became millions. So, how many stars are actually in the Milky Way? This is harder to answer than you might think, and the difficulty reveals something important about the challenge of counting cosmic objects. First, we can't see most of our galaxy. Dust clouds block our view in many directions. When you look toward the galactic center, you're peering through thousands of light-years of dust. It's like trying to see through fog. The light from distant stars gets absorbed before reaching us. Second, most stars are dim, really dim. Red dwarf stars, which make up about 70 to 75% of all stars, are so faint that none are visible to the naked eye despite being extremely common. If you could see all the red dwarfs in our local region of the galaxy, the night sky would be packed with stars, thousands of them where you currently see dozens. Third, we're inside the thing we're trying to measure. Imagine being in the middle of a dense forest and trying to count all the trees. You can count nearby trees fairly easily, but distant ones are hidden behind the ones closer to you. And the forest extends in all directions beyond what you can see. Astronomers use several methods to work around these problems. They count stars in small regions where they have good visibility and multiply by the total area. They measure the total mass of the galaxy using gravitational effects and estimate what fraction of that mass is stars versus gas, dust, and dark matter. They study other spiral galaxies similar to ours and use those as templates. All methods have uncertainties, but they converge on a consistent range. The Milky Way contains between 150 billion and 250 billion stars. Most estimates cluster around 200 billion. 200 billion stars in our galaxy alone. If you counted them at 1 per second, it would take over 6,000 years. You'd need to have started counting before the pyramids were built. Think about what this means. You can see maybe 4,000 stars on the darkest night, but they're swimming in a sea of 200 billion stars you cannot see. For every star visible to your naked eyes, there are 50 million invisible ones. The galaxy is incomprehensibly more populated than the night sky suggests. Now, here's where things get truly mind-bending. For most of human history, people didn't know other galaxies existed. When astronomers in the 1700s and 1800s looked at fuzzy patches in the sky, they called them nebulae and assumed they were gas clouds within the Milky Way. Some were indeed gas clouds, but others were something far more extraordinary. The Andromeda Galaxy is visible as a faint smudge to the naked eye on dark nights. For centuries, it was just another nebula. Then in 1923, Edwin Hubble made a discovery that revolutionized our understanding of the universe. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble found a Cepheid variable star in Andromeda. Cepheid variables are pulsating stars with a special property. The time it takes them to brighten and dim is directly related to their actual luminosity. Measure the pulsation period and you know how bright the star really is. Compare that to how bright it appears from Earth, and you can calculate its distance. When Hubble did this calculation, he got a shocking result. Andromeda was roughly 900,000 light-years away in his initial estimate. We now know it's actually 2.5 million light-years distant, or about 14.7 quintillion miles, roughly 23.7 quintillion kilometers. His measurement was off because he didn't know the exact relationship between period and luminosity. But the key point was established beyond doubt. Andromeda couldn't possibly be inside the Milky Way. It was an entirely separate galaxy, a whole other collection of hundreds of billions of stars, existing far beyond our own. The universe, in that moment, became incomparably larger than anyone had imagined. The Milky Way wasn't the universe. It was just one galaxy among many. Once astronomers knew what to look for, they found galaxies everywhere. Point a telescope at any patch of seemingly empty sky, and you'd find dozens, hundreds, sometimes thousands of galaxies. The universe was filled with them, but how many? And more importantly, how many stars did all those galaxies contain? In the 1990s, astronomers conducted an audacious experiment. They pointed the Hubble Space Telescope at a tiny patch of sky in the constellation Ursa Major. This patch appeared completely empty to the naked eye, and even to most telescopes. It was so small it could be covered by a grain of sand held at arm's length. Hubble stared at this empty patch for 10 days straight, collecting every photon of light that reached it. The resulting image was called the Hubble Deep Field, and it was revolutionary. In that tiny empty patch, Hubble found about 3,000 galaxies. 3,000 whole galaxies in a region of sky you could cover with a pinhead held at arm's length. Most were incredibly distant, billions of light-years away. Their light had been traveling for most of the age of the universe to reach us. Do the math. If there are 3,000 galaxies in such a tiny region, and you need about 12 million such regions to cover the entire sky, that suggests tens of billions of galaxies in the observable universe. Later observations went deeper. The Hubble Ultra Deep Field found about 10,000 galaxies in an even smaller patch. The Hubble Extreme Deep Field pushed deeper still, and in 2016, a team analyzed all available data and arrived at a new estimate: about 2 trillion galaxies in the observable universe. This number comes primarily from data collected between 2010 and 2020. The James Webb Space Telescope, which began operations in 2022, is still refining these estimates. Early results suggest the count is in the right ballpark, though some very distant, faint galaxy populations may have been missed in earlier surveys. Think of this as our best current estimate, accurate to within perhaps a factor of 2 or 3. 2 trillion galaxies, each one containing anywhere from a few billion to over 1 trillion stars. The diversity is staggering. Dwarf galaxies with only a few billion stars. Spiral galaxies, like the Milky Way with a few 100 billion. Giant elliptical galaxies with several trillion stars each. What's the average? If you weight by stellar mass and account for the many small galaxies we know exist but are hard to detect, the typical galaxy probably contains around 70 to 100 billion stars. Let's use 100 billion as a round number, acknowledging that this is approximate. 2 trillion galaxies times 100 billion stars per galaxy equals 200 billion trillion stars. Written out, that's 200,000 million stars. In scientific notation, it's 2 times 10 to the 23rd power. Let me try to give you some perspective on this number, but I'll warn you up front. It won't really work. The number is too large to grasp intuitively, but we can at least try to gesture toward its magnitude. There are approximately 7.5 quintillion grains of sand on all of Earth's beaches. That's 7.5 billion trillion grains. For every grain of sand on every beach, there are about 27 stars in the observable universe. Some popularizations say 30 stars per grain. Others say closer to 10. The exact ratio depends on which sand estimate you use, but the order of magnitude is correct. Roughly 10 to 100 stars for each grain of beach sand on Earth. Pick up a handful of sand next time you're at the beach. You're holding perhaps a few thousand grains. For each one of those tiny specks, there are dozens of stars scattered across the cosmos. Each star, a massive ball of nuclear fire, most likely surrounded by planets existing in a galaxy somewhere in the observable universe. If every person currently alive started counting stars right now, and each person counted 1 star per second without stopping, it would take humanity nearly 800 years to count them all. Generations would be born and die during the count. Entire civilizations could rise and fall, and we'd still be counting. But here's what makes this even more extraordinary. That number, 200 billion trillion stars in the observable universe, might be a dramatic undercount of the total number of stars that exist. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travels at 186,000 miles per second, or 300,000 kilometers per second. In 13.8 billion years, you might think light could travel 13.8 billion